So this is Griffiths Electrodynamics, problem 5.17. What we're looking at are two charged flat surfaces, a plus surface area, or surface charge density of plus sigma on the top and minus sigma on the bottom, and they are actually translating through space with some velocity v, which is the same for both plates, so they're just matching pace with each other. And what we need to do here is find the magnetic field that results from this, and also what we're interested in are the magnetic forces between the two and the electric forces, or force per unit area between the two. So just a quick physical idea of what's going on. If we have two currents going the same direction, they're going to attract each other. Since one of these has opposite charge, one of the currents is pointed the other way, and they're going to repel each other. But because they're oppositely charged electrically, they're going to attract each other. So magnetically they're repelling, and electrically they are attracting. And the question is, how fast do they need to be going for these two forces to balance each other so that there's no net force on the plates? Okay, so first we're going to look at the magnetic field of this. I made up a little drawing of an Amperian loop here. All right, so if we have, just looking at the top plate, say, so we have a plus sigma, and it's going in this direction. If we draw a little Amperian loop intersecting some length, which I will call L, of this surface, then our little loop, our integral around this is going to be multiplied by 2L. Right? The B goes to, or B is, we know it is going to be, the dot product between B and DL is going to be 0 for these lengths here on the sides, because the B is orthogonal to the direction that we're integrating. So all that counts are the top and the bottom. There's one of each, and we get a B and a 2L. All right, and what is the, so we have our permeability of free space here. What is the enclosed current? Well, that would be L multiplied by sigma multiplied by V. Or we'll just use the speed in this case. Again, at the end we'll get that direction from the right-hand rule. Okay, so fortunately our L cancels out, because that's just arbitrarily chosen by us anyway. This L could be large or small. It shouldn't matter to the problem, and so fortunately that cancels out for us. B equals mu naught sigma V, and then divided by 2. Okay, and this is the magnitude of B. Let's find its direction by the right-hand rule. So if our charge is moving to the right, the field is going to curl around this way. So that means that B will be coming this way above the plate or the surface, and going the other way below the surface. So let's go ahead and draw that on this picture here. So we have our top plate here, and where am I? So looking at this top plate, looking at these arrows, we see that above the surface, B is pointed out of the page. So I'll draw sort of the arrow pointing towards us. And below the surface, B is pointing into the page. And that also counts for down here. And because this surface is infinite, you can't really tell how far away you are from it, right? So this is a constant magnetic field, meaning it's the same strength no matter how far away you go, because the surface is infinite, all right? Or we're pretending we're very close to a large surface, so it looks infinite. What else? Yeah, I think that's about it for that one. All right. If we were to go through the same process with the Amperian loop for the same V direction, only a minus sigma, well then we would just get this minus sigma. We just plug in a minus sigma instead of sigma for all of this, and we just get a minus sign right here, which makes sense again if you look at the right hand rule. So suppose we had minus charge going this way, which is you know, you could use the left hand rule if you want, right, for minus charge, all right, and you would see that it points the other direction on top and bottom, but has the same magnitude. So from this plate down here, we get the same magnitude of B, but in the opposite handedness, all right? So before, it was above the plate, it was coming towards us, and below the plate, it was going in. For this one, above the plate, it will be coming or going away from us, and then below the plate, it will be coming out. So let's draw that in. Now you'll notice this is exactly what we did for the case of capacitor, right? When you use Gauss's law, you know, something like this that we'll use in a moment. And you do this for an infinite plane capacitor, you also get this sort of thing where what happens is the outside will cancel out because they're going opposite directions with the same magnitude, but the inside adds together, so you actually get a field twice as large here on the inside. So the field for the inside, I'll go ahead and put a vector on it now, and it's just 2 times this. So mu naught sigma v, which by the way, sigma v is equal to k, right? So mu naught times the magnitude of k, and for the vector part, I'm just going to draw this, the tail of the arrow pointing into the page. All right. So now let's talk about the force per unit area and how do we get these two to balance. So which one should we do first? Let's, I think we'll do magnetic force first. All right, so skip to a new page here. The magnetic force, which we'll call big F, we just use the Lorentz force law. Q multiplied by V cross B. What is Q? Well, we're going to have to look at some area, right? Some area of this surface charge density. And so Q is just going to be equal to sigma multiplied by that area. That's equal to Q. We should first talk about what we're doing here. So the way I'm going to find force per unit area is I'm just going to look at the magnetic field from the bottom plate, and then find the force on the top plate from that magnetic field. All right. There's probably other ways to do it. Using, for example, this twice as strong magnetic field that we found is if you take the magnetic field for both plates. There's other ways to do it. You could look at the energy density of the configuration and then take the derivative to get the force. But we'll just look at it this way. All right. So looking at the top plate, what did we say? It's going to be repelled from the bottom plate magnetically and attracted electrically. So, all right, so we need V. Let's just double check really quick. This cross product, they are perpendicular to each other, so we won't get any like sine of theta or anything in there. So we know we're just going to get V, B, just the magnitudes of the two. But what direction is it going to be in? Let's just double check our V cross B. So in between the plates, we said the field is pointed inward, and that's also the same, of course, if we're only looking at the field from the bottom plate. So if V is going this direction and we cross it into the page, our thumb points upward, which is repelling. So this is a repelling force. Okay, I wrote this let's make this a vector up here, and then let's just talk about the magnitude of it, and I'll just put repelling in parentheses so we remember what we're doing. Let's go ahead and plug in what we found for B. Remember, we're only looking at the magnetic field from the bottom plate, so it's actually 1/2 of this. We only look at one of these, not the other one. So it's what we found right here. Or in other words, mu k divided by 2. So we have a sigma A V and then mu naught k divided by 2. Okay, and we could express this, let's just write both forms, because k was sigma V, so a sigma squared V squared with a mu naught. See if I can write properly. K, a sigma squared V squared mu naught A over 2. That's another way of writing it. So let's go ahead and write little f is equal to the force per area. Okay, and to get that, we just divide by A on both sides. And let's just use this version real quick. So mu naught sigma squared V squared over 2. And let me write a little mag on this. We remember we're looking at the magnetic contribution to the force, or the total force. Now, and that's important because now we're going to look at the electric contribution. So, what is the force electric? Well, that would just be the force on a charge is just equal to the electric field, right? Multiplied by that charge. So we need to find E now. We found B already, now let's find E. For that, we're going to use our Gaussian surface, all right? And our little arbitrary parameter here will be A instead of L. Remember, L divided out, well, A is going to divide out too. I didn't leave myself very much room, but maybe I can work in this space down here. All right. So and it's just going to be like a capacitor, right? So This integral here, we have b, and then we have 2a, right? Again, the top and the bottom are going to contribute, but the sides are not because of this dot product. These two things are orthogonal for the sides. And let's see. I wrote this wrong. I was like, why do I have a B here? B is not orthogonal to the sides. Like, sorry about that. This is an E. Well, that's embarrassing. Gee, okay. I guess I just looked at this and like copied it right down. Wow. Didn't even notice till now. E multiplied by 2a is equal to the charge enclosed, right? Which sigma multiplied by a over epsilon naught. So this tells us that E, the magnitude of E, is equal to, we can divide out these A's just like we promised, sigma over 2 epsilon naught. Right, just the electric field due to an infinite, sheet of charge. We could have just remembered that, right? And of course, if you work this out for a capacitor, right, you do the same thing as this, where they cancel out above and they double inside, and inside a capacitor, the electric field is just sigma over epsilon naught. But again, what we're looking at is the force on the top plate due to the charge on the bottom plate. So what we're doing here, we've got the charge of the top plate is sigma multiplied by some A, right? And the electric field due to the charge on the bottom, we had a minus sigma over 2 epsilon naught. Okay, so comparing this to our magnetic version, well, let's go ahead and what will the direction of this be? Well, it's attractive, right? So I'm just going to write down, and just to be cute, let's put a hat on top of that, so it's just the down vector. We could have called it z or minus z or whatever we wanted. Let's just say down, meaning attractive. Okay. So this is equal to minus sigma squared A over 2 epsilon naught. Now let's write it just like we wrote for the magnetic force. Let's write force per unit area. Oh, here I go again. Writing magnetic. Okay, and then I'll just write the magnitudes once again. Right, the magnitude of this sigma squared A 2 epsilon naught, and then I'll put in parentheses attractive. Okay, so our question originally, right, was what speed do these plates have to be traveling in order for the electric force to balance with the magnetic force? So here we have a repelling force per unit area and an attractive force per unit area. Let's set them equal to each other, meaning they're balanced, and see what we get. So here we have, I'll write the magnetic one, mu naught sigma squared v squared over 2. And now the electric one, sigma squared A Did I leave off an A? Oh, I forgot to, wow, lots of mistakes today. I forgot to divide by A, right? I divided the A out of this. There should be no A here. Say it's supposed to go away. Over 2 epsilon naught. Okay, so our sigma squared goes away. So notice there are no sigmas left in the problem. So it doesn't matter what the charge is on these two plates. It doesn't matter if they're slightly charged or very heavily charged. All such systems like this will go the same speed in order for these two forces to balance. What do we have left? Oh, we can multiply a 2 on both sides. And let's, we have a v squared is equal to, we just have to divide both sides by mu naught. 1 over mu naught epsilon naught. Okay, so our speed at which these balance, you know, it could be either direction, whatever, any direction you choose, as long as it's oriented sideways to the plates. So this way, whatever. 1 over the square root of mu naught epsilon naught, which is equal to the speed of light. So that's the big shocker here, right? The way in SI units and stuff, rather than Gaussian units, all of this stuff works out is the magnetic force is smaller than the electric force. And the way to make them equal is if the currents are traveling at the speed of light. So anyway, that's kind of the aha moment.